All right, this is the last lesson of Unit 10 on exponential and versus linear functions. So we're going to be talking about exponential decay, which is the exact opposite of exponential growth. So remember, if something is growing exponentially, it will end up looking like this right here. So if you have exponential decay, it's just going to look like this. So it starts off declining very rapidly, and then it starts to level off, okay? So let's take a look at what we have in example number one. In example number one, it says that John bought a new car for $15,000. As he drove it off the lot, his friend Will told him that the car's value just dropped by 15% and that it would continue to depreciate 15% of its current value each year. Depreciate means to go down. If the car's value is now $12,750, according to Will, what will its value be after 5 years? So at the beginning, the value was $12,750. That's because it went down by 15%. So you figure out what 15% of $15,000, and then you subtract that from 12,750. Then we're going to do the same thing after the initial decrease, and we are going to figure out what the next amount is going to be. So we figured out that if you do this on your calculator, if you figure out what 15% of $12,750 is, so type this into your calculator, $12,750, multiply that by 15%, and you end up getting this number right here, which we have right here. So go ahead and check in your calculator. Please make sure that this is really truly what you would get. Please make sure you are actually doing this in your calculator and you're not just watching it. So then what you have to do in your calculator is figure out how much the car is going to be worth, because it dropped $1,912.50 in that year. So subtract it, and that's how you end up getting this value right here of $10,837.50. Okay, we'll do one more year together and then we'll see how you do on your own. All right, so let's go ahead and do the same thing with year one. So in year one, we figured out it would be $10,837.50. So I'm going to take that amount and I'm going to figure out what 15% of that is. So plug this into your calculator, and you should end up getting $1,625.63. Okay, then you subtract that from 10,837.50, and you end up getting your new answer of $9,211.88. So what we'll fill in right here is $1,625.63. And then we'll say right here that this is $9,211.88. All right. I would like for you to finish up the rest of this chart, so we know this is going to start at $9,211.88. Please actually do the workout, and then we will go ahead and compare your answer with mine, see how you do. So please check the chart that I have here. If you need to press pause to make sure that you have the right values, go ahead and do so. One thing I want you to notice is that each time a year passes, the amount of money that is lost on the car decreases. And that follows the pattern that we talked about earlier. When it's exponential decay, it will end up looking like that, as opposed to growing exponentially the other way. Okay? And then one other thing that I just want you to notice is that you could have just taken $12,750 and multiplied that by whatever's left over after a 15% decrease, which means that you'd be paying 85% of the total price. So go ahead and plug that into your calculator. You will notice that you end up getting $10,837.50. And then if you take $10,837.50, multiply that by 85%, because that's how much you are paying again, you'll end up getting the $9,211.88, so on and so forth. Okay, so let's just do a quick reminder of the formula when you have compound interest. So normally when you have compound interest, we said that the equation would be f of t equals p, the principal, the initial amount, multiplied by 1 plus the rate raised to the t power, okay? Where t is the amount of time. And then also remember that generally exponential growth is a times b to the t power. But this only works if b is greater than 1. Okay. Now question B asks you to write an explicit formula for the sequence that models the value of John's car t years after driving it off the lot. So normally we would use this formula right here, where it would be f of t equals the principal multiplied by 1 plus r to the t power. But that's if it's growing. That's if it's looking like this. But in this example, it's not growing, it's actually decreasing, it's decaying. So here's your difference. Instead of saying f of t equals p times 1 plus r to the t power, go ahead, take a guess what you think we should do. If you said subtract, you are absolutely correct. So this means that the formula would be f of t equals our p-value, our principal amount, at time 0 is 12,750, multiplied by 1 minus the rate, which is 0.15, to the t power, or I could just say f of t equals 12,750 multiplied by 0.85 to the t power. Okay, now if you notice, we ended up multiplying by 0.85 repeatedly every single time. Just like when we had compound interest, we would multiply by 105%, for example, would be 1.05. We would multiply it by 1.05 repeatedly. Here we would multiply by 0.85 repeatedly, and that's why it's raised to the t power. However many years there are is the number of times you multiply by 0.85. Now, if you notice, this formula very closely resembles the formula for exponential growth right here, where A is the initial amount, so 12,750 is the initial amount, B is your growth factor, except here our growth factor is actually not going to be greater than 1, it's less than 1, and that's why it is decay. So let's answer question C. Using your formula from part B, or use the formula from part B to determine the value of John's car 5 years after its purchase. Round your answer to the nearest cent. So let's go ahead and do that. So I'm going to do f of 5 equals 12,750 multiplied by 0.85 raised to the 5th power. Go ahead and plug that into your calculator, see what you end up getting. You should end up getting f of 5 is equal to $4,808.66, okay, which is exactly what we got before. So remember, we can use the formula to get this answer instead of repeatedly doing this problem where you multiply by 0.85 over and over again. So compare the value with the value in the table. Are they the same? Yes, they are the same. Okay. Use the formula from part B to determine the value of John's car, 7 years after its purchase. Round your answer to the nearest cent. Go ahead and try this yourself. Press pause and then come back and see how you did. All right, so I'm going to do f of 7 is equal to 12,750 multiplied by 0.85 raised to the 7th power. Plugging that all into my calculator, I'll end up getting $3,474.25. So just after 7 years, your car that was originally that you bought for $15,000 is worth less than $3,500. Okay, so it's really big how much it decreases by, but eventually it will start to level off. So how is exponential decay like exponential growth? It's basically the same thing, except instead of a b value greater than 1, like we talked about right here, the b value is going to be less than 1. So it's the same, except it is the same. That's an it, not an h. It is the same, except the growth factor is less than 1 as opposed to greater than 1. So B would be less than 1. And remember, if it looks like this, let me draw that a little bit better. If it looks like this, it is exponential growth. And if it looks like this, it is exponential decay. All right? Now, you may be surprised to find out that that exponential growth and exponential decay occur all the time in real life, like times that you probably don't even realize. Even, for example, those of you guys who have been following March Madness, the way that the teams are eliminated is by exponential decay, because you start with a large amount and you are decaying by 50% in each round. All right, so let's go ahead and take a look at question number 2. Identify the initial value in each formula below and state whether the formula models exponential growth or exponential decay. Justify your response. So in question A, our initial value, our starting amount, is going to be this 2 right here, because that's the A value, it's your starting amount. So we're going to say that A is 2. And then I have to look at the B value. Now, is the B value greater than 1 or less than 1? If it's 2/5, it's less than 1, so that means that it's going to be exponential decay. And then our reasoning for it is that B is less than 1. Okay, so let's do question B together. In question B, our initial value is 2/3. Now, our initial value has no effect on whether or not this is exponential growth or decay. It all has to do with this term right here, this B value. So this B value is also less than 1 again. So we're going to say that this is decay. And the reason why is because B is less than 1. Go ahead, try C, D, and E. See how you do. And then come back and compare with me with your answer. Don't forget to press pause. All right, go ahead, compare C, D, and E with my answers. For C, you should get that the initial value is 2/3, and it is exponential growth because B is greater than 1. For D, you should get A is 2. It is also exponential growth because B is greater than 1 again. And then for E, it is the initial value is 3/2. It is exponential decay because the B value is less than 1. All right, here's an example of a real-life situation in which exponential decay happens, just like the example that we looked at with the car's value depreciating. When you take medicine, the amount of medicine that's in your body decreases by a certain factor, and so after a while, it'll eventually taper off. So let's take a look at question 3. Kelly's mom takes a 400 milligram dose of aspirin. Each hour, the amount of aspirin in a person's system decreases by about 29%. How much aspirin is left in her system after 6 hours? So we're going to use the exponential decay formula. So the initial value is 400. Now the question is, what is the B value? Well, the B value is how much it's decreasing by. So it's going down by 29%, which means that there is 71% of the medicine left in your system, which is 0.71. So this right here is your B value, okay? So I'm going to say that the answer, or the formula, is going to be 400 multiplied by 0.71 raised to the t power. So I'm going to figure out what f of 6 is because it asks you after 6 hours. Okay, so it's 400 multiplied by 0.71 raised to the 6th power. Go ahead and plug that into your calculator, and you will see that after 6 hours, it goes from a whopping 400 milligrams to just 51 milligrams because, again, it decreases pretty fast at first, and then it starts to taper off, level off. Okay, so your answer to this question is 51 milligrams. All right, number 4. According to the International Basketball Association, a basketball must be inflated to a pressure such that when it is dropped from a height of 1,800 millimeters, it will rebound to a height of 1,300 millimeters. So Luke decides to test the reboundability of his new basketball. Let f of n be the height of the basketball after n bounces. Before we do this, I just want you to realize that if the basketball drops from a certain height, eventually, the rebound height will get shorter and shorter and shorter, and if you're to map it out, it looks just like exponential decay, which you will see shortly. So let's look at question A. Assume the ratio of each rebound height to the previous rebound height remains the same. What is the ratio? So I'm going to take my current rebound height, which is 1300, and I'm going to do it as a ratio to my previous rebound height, which is 1800. So that means that my ratio in simplest form would be 13 over 18, which hopefully you will recognize is the B value because this is your growth ratio, okay, or your decay ratio actually. All right, so question B, complete the table below to reflect the heights Luke expects to measure. So I would take my first value, which is 1800, and I would multiply it by my ratio. So if you multiply 1800 by 13 over 18, you'll end up getting 1300, which is what the height would be after one bounce. Okay. Then to figure out the next one, I would take 1300 and I would multiply that by 13 over 18 and see what I get for that. And when you multiply that value, you'll end up getting 939 right here. Okay, so this right here would be 939. Then you would do the same thing for the third bounce. You would take 939 and multiply that by 13 over 18, and you would keep going. Go ahead and fill in the rest of the chart, press pause, and then come back to me to see how you did. All right, so these are the values that you should get. You should get 678, and then you should also get 490. All right, and those are all measured in millimeters. So question C says, write the explicit formula for the sequence that models the height of the basketball after any number of bounces. So remember, you're repeatedly multiplying by 13 over 18 right here. So this value right here is what is your, remember we said is your B value, it's your growth value, and think about what your initial value is. What I want you to do is try to write it out yourself, and then when you're done, compare with my answer to see how you did. All right, you should get that f of t is equal to the initial value, which is 1800, multiplied by the growth ratio, which is 13 over 18, all raised to the t power, because you are repeatedly multiplying by 13 over 18. Question D asks you to plot the points from the table, so we'll go ahead and do that. So I'm going to take my first bounce occurred at 1800, so I'm going to put a dot right at 1800. Excuse me, it started at 1800. It was not after the first bounce. After the first bounce, it was at 1300. After the second bounce, it was at 939. Okay. After the third bounce, it was at 678. After the fourth bounce, it was at 490. And you know what? I would like you to try a couple more bounces, see what you end up getting. So go ahead and go up to maybe the sixth bounce, see what you get. So I got that after 5 bounces, the height would be 354, and that after 6 bounces, the height would be 255. Okay, so I'm going to put a dot right at 354. And then I'll put another dot at 255. Okay. So if you notice, it definitely appears to have an exponential decay pattern as you graph this all out. All right. So the question is, or the last question that we have, is asking you to use the curve to estimate the bounce number at which the height will drop below 200 millimeters. So go ahead and take a look and see what you get. Where do you think it'll drop below 200 millimeters? Write down your answer. So I'm going to guess after 7 bounces that it will drop below 200 millimeters. And it's just a guess based on my graph. So then I'm just going to check to see if it works. So I'm going to figure out what f of 7 is. So I'm going to take 1800 and multiply it by 13 over 18, all raised to the 7th power. And then I will see what that will give me when I plug it into my calculator. And you will get about a height of 184 millimeters, which seems to be the bounce number that will get you to drop below 200 millimeters. All right, hopefully that all makes sense, and I will see you next time in class.